So what are you guys?
We're the Smartwood family.
Hi guys. So we had a request from one of our students, and she saw the video balls and boxes. So let me write that up here. Which really talked about multi-choose. So, I'm going to give you one interpretation of multi-choose just to remind you. But this video is going to be a little different. I love explaining things from scratch, but that would make this video incredibly long. So I think basically I'm going to assume that you're comfortable with multi-choose. Okay? So sometimes multi-choose is written like this, but the idea is basically if you have n boxes, okay, and k balls, and the key here is that the boxes are distinguishable, but the balls are not. I'm going to go ahead and label the boxes from 1 to n so they have names, and we can tell them apart. The other thing is, because they have names, they kind of have this natural order, right? You can imagine the leftmost is box 1, and the rightmost is box n, okay? Basically, you can interpret this guy in terms of binomial coefficients. So it's going to be this, like that, or like this, same thing. One of our students noticed that basically you can formulate like this. So she saw this in her textbook. So n times n plus 1 dot 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 n plus k minus 1 over k factorial. Okay. So one thing is, because it's so pretty, she basically looked at this and went, wait a minute, is there a way to interpret this directly? Like, is there some intuition behind this formulation of it? So, everything I've ever seen has been like this. So you do the argument with balls and boxes or stars and bars. You write this as a binomial coefficient, which is n plus k minus 1, choose n minus 1, or this version, right, over here. And then when you translate this stuff, you just compute it, you get this, okay? But I kind of agree with her. So I looked at this and went, maybe there's some pretty interpretation or one we can come up with. So what I'm going to give is sort of my interpretation of this, and hopefully this is going to help. But basically what it is, I debated a little bit. So one was, should we make this kind of formal? So we can have a formal proof and you kind of see like, oh, okay, this interpretation works, blah, 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 blah. But then the video might be overly long, especially if I try to add like the intuition behind it. So my thinking is kind of this. What our student wanted the most was intuition, right? The connection, like why is it n times n plus 1 dot 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 n plus k minus 1? Which in a weird way is kind of the reverse of this. So if you did the regular binomial coefficient thing and choose k, this can be written as n times n minus 1 dot 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 n minus k plus 1 over k factorial. Okay, so that top formula, this one right here, I'm going to write it one more time. It just looks so pretty. There must be some nice way of interpreting this. Again, I've never seen one myself, so I'm going to give you my formulation of it. And what I'm going to do is I'm going to try and make it as, a bit concrete, so we understand like what I was thinking, what the motivation was. That's the main point, right? And if you want to make it formal, it's not very hard to do that after seeing this video. Okay, so here's my thinking. Basically that bottom is k factorial, right? And that k factorial is just so nice because if you have k balls that are distinguishable and you put them in a line from left to right, then they're exactly k factorial ways of arranging them. Okay, so we've talked about this in other videos, but it just as a quickie repeat because I think this is important. If you look at A, B, and C, and so here k would equal 3 guys, right? How many ways can you arrange them? Well, the claim is 3 factorial. And that's because you can think of 3 slots. Slot 1, 2, and 3. And what you have is 3 choices for slot 1. So let's say we picked A, okay? Then once you've chosen that, how many, so 3 options for slot number 1. How many options do you have for slot number 2? Well, you have 2. You have B or C, right? So I'm going to put down B to make it concrete. So 2 options there, okay? And then how many options do you have for that final one? Well, you only have 1 choice. And in this particular case, it's C, okay? So in the middle of making choices, we multiply, and we get exactly 3 factorial, which is 6, okay? A way to see that directly would be, okay, for the first slot, slot number 1, right? How many options do you have? We have 3 choices, A, B, and C, right? So this idea is going to be used throughout. This idea of picking one just to see concretely what's going to happen next. Once you pick one, you have 2 options for the second slot, right? So this one right here. So in this case, you can have either B or C, right? I'm going to follow this line of logic. And then once you pick that, there's only 1 choice for the remaining slot. So here we'll make this go C, because then you have A, B, C, or A, C, B, right? Okay, again, if we follow this pattern, for B there were 2 choices. There's either C or A. For C, there are two choices, A or B, right? And then for that final slot, there's really only one choice, A, C, B, A, like this. And you can definitely see that what's happening here is we have three choices for the first, right? Two for each of those. So you're multiplying by 2 to get 6. And then for each of those, one choice. So you're multiplying by 1 to again get 6. Okay? All right. Again, if you're comfortable with this, sorry for rehashing it, but I just wanted to make the point that this really was the start. Like when I saw that guy right there, it gave me an idea. It motivated what we're about to do. So, the end boxes are definitely distinguishable. Okay? But what I want to do now is I want to pretend that the K balls are distinguishable. And I want to put an ordering on them. Okay? And that's actually motivated, let's draw this line here, by this K factorial thing. Because what we're going to do is we're going to count this way, and I hope this way will be easy. And then once we finish counting this way, we will divide out by K factorial so that the ordering doesn't matter anymore. Okay? Because remember the original problem, you can't distinguish the balls, so order doesn't matter. Okay. All right, so let's try this out. And I want to be very clear. So I'm going to label the boxes, box 1 through box n, and I'm going to draw them like this. And to make this concrete, if you want, we can say n is 30. Okay? And then we're going to have the balls. And I'm going to give the balls names because we're going to assume we can tell them apart. So there's ball number 1 up to ball number k. Again, to make this concrete, I'm going to say k is 10. Okay? All right. So let's start the procedure. And I think it's more important to follow the procedure because once you get the idea from case number 1 and case number 2, then you're good. Okay? So let's talk about ball number 1. Okay? This is pretty mellow. So you've got your 30 boxes, right? Okay, so n is equal to 30. And you're going to place ball number 1. So how many options are there for ball number 1? That's pretty easy. Ball number 1 really has 30 choices, right? It can go in any one of these. And that would be it. Everything is good. Okay? So I'm going to note here we have n choices for ball number 1. Okay? Now it starts to get a little bit more interesting. Let's look at ball number 2. So again, just like up here, where to visualize what's going on, I would fix one of them. It could be A, B, or C, but I fixed A to see how many options from that we had, right? We're going to do something similar. So I'm going to pretend we've placed ball number 1, okay? So maybe we have 1, 5, and then box 30, okay? And I'm going to assume in every case we're going to look at, the ball number 1 has been placed in box number 1, okay, just to make it simple. Okay, so now when I think about this, how many choices, right? How many choices do we have for ball number 2? Well, ball number 2 can go basically in any one of these, right? So excluding box number 1. So it can go in 29, so it can go in 29 boxes, okay? But you can definitely put in box number 1, okay? The only issue is that if you put in box number 1, remember, we assume not only that you can distinguish the balls, but that we can put an ordering from left to right on them, okay? So if, for example, ball number 1, let me write this now. Ball number 1 had been in box number 1, and we place ball number 2 in box number 5, there's definitely an ordering, right? Because ball number 1 is to the left of ball number 2. There's no problem there. The issue comes up if we pick box number 1. So if you pick box number 1, ball number 1 is already here, right? And if you put ball number 2 there, everything's great. It's just that I don't know who's first. Who's to the left? Is it ball 1 or ball 2? So we're going to take care of that. We're going to assume, so again, let's go back to this, that you're picking one of these boxes. We already know what happens if you pick box 2 to box 30. You just put ball number 2 there. If you pick box 1, which is where ball 1 happens to be, so wherever ball 1 is, if you put it in the same box, what that means, we're going to assume, is that you put ball number 2 in the first position. So it is to the left of ball number 1. Okay? So now if we look at this, we have, again, 30 choices. That's really n, right? You can say it more succinctly like this. Whatever box number you pick, you put that ball number 2, right, in the first position in those boxes. First meaning to the left. So you put in the leftmost position in that box. Okay? So now the only thing to ask is, have we left anything out? We've taken care of almost all the possibilities, right? You can put ball number 2 in box 1 through 30, no problem. And we've taken care of the case where you put ball 2 where ball 1 is, right? The assumption being the ball 2 is always going to be to the left of ball 1. Okay. The only thing we haven't taken care of is What if you're in box number 1 with ball 1 again, except instead of being to the left, you're to the right of it, which is a definite possibility, right? Okay, so that's one more option. So instead of having 30 choices or n options, what you really have is n plus 1 options, right? Now, if you want to do that, you can visualize it by actually having boxes 1 through n, and then this kind of imaginary box, n plus 1. Or if you put ball number 2 in the n plus 1 box, what that really means is wherever ball 1 is, so in this case I think it was in box 1, right? You're going to put ball number 2 in the same box, but you're not going to put it to the left this time, you're going to put it to the right. Okay? So being in here is equivalent to being to the right of wherever ball number 1 is. Right? No big deal. Okay, but this is the key step, because if you understand what's going on here, then this final part will be a piece of cake. Okay? If not, it's going to be pretty stressful. But so here's my thinking on this. If you're doing this formally, we probably do it by induction, and then we look at the general case. Okay? Since I'm not going to do it formally, I'm just going to go all the way to the last ball, ball number K, to make my point. Okay? Now remember, if we're placing ball number K, what does that mean? Following our procedure. That means we've already placed K minus 1 balls. Now if you want to make this concrete, this is going to be ball number 10. And we've already placed balls 1 through 9. Okay, they're already there. Okay, and we have an ordering. So all the balls are arranged from left to right, and any 2 balls are in the same box. You can tell who's to the left and who's to the right, like what their positions are. Okay? All right, so now let's assume, I'm going to pick a generic setup, that we have balls 1 through 9 placed, and they happen to look like this. Let's put 10 here. Let's put 30, so n is equal to 30. Okay. And then let's place these one in here. So let's say that what? K is 9, so we place 9 balls. So let's do 1, 2, 5, 8, and 9. Okay, so something like this. Okay, so these are all the balls that are placed, and and all the other boxes are empty. So we placed all 9. Now we're placing the 8th or 10th ball in. Okay, all right. So what's our rule going to be? All right. Well, first there are n choices, because you can pick any of the boxes 1 through 30. Okay. So if you pick one of the boxes 1 through 30, we're going to follow the same procedure. What that's going to mean is that we take our ball, let's say right here, the 8th ball. So say we pick the number 5. Okay. Same conventions before. What does that mean? That means we're going to put the ball in box number 5, but it's going to be in the first or leftmost position, guaranteed. So definitely what we're taking care of is 30 choices, where we put you in one of those boxes, and whichever box you place into, you're in the leftmost position. So done. Okay? All right. But now the question is this. What about these extra choices? Because you can see the pattern. For the first ball, there were just n possibilities. So n. Okay? For the second ball, I should have made that clearer, there were n plus 1 possibilities, right? Because over here, n plus 1, there were those n choices, and the other option that came from placing ball number 2 to the right of ball number 1 in the same box. Okay? So if this pattern is going to hold up, remember it's like n times n plus 1 times n plus 2 times n plus 3 dot 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 times n plus k minus 1. I'm thinking this is probably where we should be. But let's see. So where are those extra choices coming from? Well, just like before, let's go back and pretend. So if I place the 8th ball, so if I place the 8th ball right here, so if I picked, right, box number 1, so let's say we pick 1, that would represent being the first ball, or the leftmost ball in urn number 1, or box number 1, sorry. Okay? All right, but there's another option. So we need to add, so we have n choices so far, and we need to add one more choice. You can think of this as the n plus 1 box, or n plus 1th box. Okay, so what is that? And so why are we adding this choice? Just like before, we're always assuming that this ball, the 8th ball, is going to be to the left of whatever's in that box, right? But over in box number 1, it could also be to the right. So we need to think of the possibility where this isn't true, right? But this is true. But that's one more option. So we're going to add that plus 1 for that. Does everybody agree? Okay. By the way, incidentally, does everybody agree? This ball here, you can think of this as counting off that extra option. There's one extra option and there happened to be one ball in that urn. Okay, but now let's pretend instead we picked box 2. So if we pick the number 2, you would end up right there in box number 2, leftmost, right? But there's another possibility. You can be in box number 2 and not in the first position or leftmost position, but you can be in the second or middle position, right? So there's another choice. And you can also be in the rightmost position. So yet another choice. So we need to add here 2 more choices, which incidentally is the number of balls in that box. Okay, so we're gonna add again +2. Okay. Okay, but anyway, let's go to box number 5. Same procedure. If you pick 5, you would have been to the left. But you have to look at the possibility of being the middle or the right. So 2 more choices. Let's add 2 again down below. Okay, you can see this pattern already. If it were box number 10, right, leftmost, but what are the other possibilities? Like 1, 2, and 3 more, so +3. What about for the final one? To the left, but it could have been to the right, so +1. You can directly add these up, right? That's going to be 9. Okay, but you can see what's happening is for every ball that's already been placed, we're getting another option, right? So since there are 9 balls beforehand, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 extra choices. So if there are k-1 balls placed beforehand, so let's do this in general, because 9 is k-1, right? Because you're placing the kth ball. So if there are k-1 balls placed beforehand, there are k-1 extra choices. So you have n choices plus k-1. And that is indeed the final one. And that really is what we think it should be, okay? So now let's write all this out. So for ball number 1, how many choices do you have? N. For ball number 2, n+1. All the way to the kth ball, which is n plus k-1. In the middle of making choices, you multiply. So we multiply all this together. Now the only issue is, what do we have in the end? We've looked at all the possible arrangements where you can tell the boxes apart, that's fine. But where you can tell the balls apart and order matters. But the issue is in the original problem, you can't tell the balls apart. And so you can't impose an ordering. So all those different orders we looked at kind of collapse. So for example, if you go back to the case we talked about earlier, ABC, ACB, right? BAC, BCA, CAB, CBA, like this. If you want to make this relevant to our case, you can think of this as being a box where you have 3 balls in there. The way we've counted, if you think of A as ball number 1, B as ball number 2, C as ball number 3, we've counted all the different ways you can order those balls, right? But the truth is, they're all the same, right? If you can't distinguish them, the picture just looks like this. So we need to collapse these. So all the different ways we have of arranging these 3 guys, they're redundant. So to fix it, we need to divide by, well, in this case, 3 factorial. For k balls, it would be k factorial. So that is it, right? The correct way of seeing this is, when you're doing the multi-choose, you can think you're placing balls in boxes, right? You can tell the balls apart. You're getting all the different orderings. You get n, n+1, ... n plus k-1, where you're forcing an ordering on the balls. But to get what you originally wanted, you have to get rid of that ordering. So why bother doing this? Because the ordering helped us count the top part, made it much easier. And then dividing by k factorial just fixed it, okay? Hopefully that helped. Please let me know if you have any questions or you think there's something up or wrong with this idea. But I feel like this is a pretty clear way of seeing intuitively, right, where this form of the multi-choose guide comes from. So hopefully that helped, and I'll see you guys next time.